What specific problem does the DISCIPL framework aim to solve regarding the limitations of current language models in reasoning tasks?
The DISCIPL framework aims to address the limitations of current language models, LMs, in reasoning tasks by enhancing their ability to perform structured inference and improve efficiency during test time computation. Traditional approaches, such as autoregressive generation, are slow and often yield unreliable outputs, particularly in tasks requiring complex reasoning. Disciple introduces a meta-reasoning architecture where a planar LM generates an ad hoc specification and inference procedure, allowing for flexible and efficient orchestration of reasoning tasks. This framework enables the decomposition of reasoning into planning and execution, which facilitates parallel search patterns and reduces computational overhead. By leveraging LMs to define inference procedures dynamically, DISCIPL significantly boosts the performance of LMs on challenging tasks, such as those in the Kali and Puzzles datasets, surpassing the capabilities of standalone models.
How does the proposed DISCIPL method work? Please illustrate the process step by step, including how it utilizes the planner and follower LMs.
The DISCIPL method operates through a structured process involving two key components: the planner LM and the follower LM. First, the user provides a natural language task description to the planner LM, which generates an inference program tailored to solve the task. This program outlines how the follower LM should be utilized, specifying the steps for execution, which may include making multiple asynchronous queries in both generative and evaluative modes. Next, the inference engine executes the generated program, attempting to produce a solution. If successful, the output is returned. If the execution fails, the planner LM is prompted again to correct the program based on the error feedback, allowing for a maximum number of retries to ensure robustness in problem solving. This iterative process enables efficient and flexible reasoning while leveraging the strengths of both LMs.
Can you provide a simple example that demonstrates the inner workings of DISCIPL, detailing how the planner LM generates an inference program and how the follower LM executes it?
In the DISCIPL framework, the planner LM generates an inference program by first receiving a user's query and then creating a code specification that outlines how to solve the task. For instance, if the task involves generating a structured poem, the planner LM, like GPT-4o, would produce a Python program that defines the steps necessary for the follower LM to execute. This program may include methods for generating text and checking its validity. The follower LM, such as LLAMA3, 2-to-1b, then executes this program, making multiple asynchronous queries to generate text or evaluate probabilities, depending on the task requirements. If the initial execution fails, the planner can be prompted again to refine the program based on the error feedback, ensuring a robust and iterative approach to problem solving.
What are the theoretical and practical benefits of using DISCIPL compared to previous approaches, particularly in terms of efficiency and accuracy?
The theoretical benefits of using DISCIPL include its ability to decompose reasoning into planning and execution, which allows for flexible orchestration of parallel search patterns, enhancing efficiency. Practically, this framework enables the planner LM to generate ad hoc inference programs that can adaptively allocate computational resources, leading to improved accuracy in tasks like Kali and Puzzles, where traditional models struggle. In experiments, DISCIPL demonstrated significant performance boosts, with the follower LM surpassing the planner on tightly constrained tasks, indicating a more effective use of resources. Additionally, by automating the generation of inference procedures, DISCIPL reduces the computational overhead typically associated with manual engineering efforts. Overall, this approach not only enhances the reliability of outputs, but also scales efficiently, making it a robust alternative to previous methods reliant on predefined scorers or verifiers.
How was the effectiveness of the DISC-IPL method validated in the experiments? Describe the datasets used, evaluation metrics, and any baseline comparisons.
The effectiveness of the DISC-IPL method is validated through experiments on two datasets: COLLI, a constrained generation benchmark with tasks defined by a formal grammar, and puzzles, a custom dataset featuring complex tasks like poetry composition and grant writing. Evaluation metrics include accuracy and coherency, with the latter assessed using the LLM as judge evaluation method, which employs GPT-4o Mini for scalable and reliable text quality measurement. Baseline comparisons are made against several models, including a planner-only approach using GPT-4o, a follower-only model, LLaMA3, 2-to-1B with and without beam search, and a frontier reasoning model, O1. Additionally, an expert program variant, DISC-IPL*, is tested to determine how well the planner can recover expert implementations, providing a benchmark for assessing DISC-IPL's performance. The results indicate that DISC-IPL significantly improves accuracy and coherency over the baselines, particularly in tightly constrained tasks.
What specific results were achieved with the DISC-IPL method on the COLLI and puzzles benchmarks? And how do these results compare to those obtained by previous models?
The DISC-IPL method demonstrated significant improvements on the COLLI and puzzles benchmarks. Specifically on COLLI, the approach allowed the follower LM to achieve accuracy levels that surpassed the original capabilities of the follower, with performance ranging from 16.3% to 59% for various models, indicating a marked enhancement in constrained generation tasks. In the puzzles dataset, which included complex tasks like poetry composition and grant writing, DISC-IPL enabled the follower to approach the performance of advanced reasoning models, such as O1, showcasing its effectiveness in generating structured outputs under constraints. Additionally, the results indicated that the planner LM's ability to generate inference programs led to better performance than using the planner or follower models independently, highlighting the advantages of the meta-reasoning framework. Overall, Disciple's architecture not only improved accuracy, but also provided a more efficient and automated solution compared to previous models.